gone, I'm not gonna be thinking about you guys, so I hope you're not thinking about me, okay?
But we will have class on this coming Monday.
No,
No.
no class, Brandon.
No
Do not
class.
do not come here.
You can come here. but
You can come
watch
here.
us.
I mean, if you guys wanna sit here and bullshit for an hour, you have this room.
Monday.
What's that?
Don't come until like.
Well, even the following Monday is President's Day.
Oh,
So we don't have class, so that's what I'm saying, a week from Wednesday is when we'll actually be here again,
Okay.
okay?
Wow.
But do feel free to bother Mike with questions about the homework, and also do feel free to email me, okay, questions about the homework. I can still help you out. It might be a little more delayed than I have been right now, but I will be there to help you, okay?
We will have video lectures.
You will have video lectures. No guarantee of when they will be when, okay? My goal is to get them all up, because I have my other class, so it's like right after this class, I'm supposed to record 6 hours. That doesn't sound fun to me. So I was going to try and maybe spread that out over the week. So my goal is to have an hour worth of lecture before this time, right, for each of my classes, so. Okay. Anything else? All right. Energy and variation, okay? What's the motivation here? Well, in previous sections, right, we derived the bar element via mechanics, right, basic principles of mechanics and materials. And we can only do that for a limited number of elements. And so we have to use energy principles and variational techniques in order to develop, right, these elements. Because as we did for the mechanics of material bar element, right, where we decided that each of the columns in our stiffness matrix, right, was a vector of forces that created a unit displacement at 1 degree of freedom and 0 everywhere else. Well, that shit gets really, really hard when you start adding, say, beam elements with multiple degrees of freedom and rotations, right? Plate elements, if you think about that, how would you decide on what that force vector needs to be for a four-sided, a four-noded plate element, right? And you were to raise that element up, right? You tell me what the forces are at the nodes, right? And so energy methods allow us, and variations allow us methods to develop those elements, okay? Energy refresher. So if we had a hill, right? And we had a ball on that hill, right? And that hill was some height h, right? This is from your physics days, right? Energy. That ball is going to have a mass m and some velocity v at the base of the hill, right? How fast will the ball be moving at the base of the ramp? Any ideas? Principle we might use?
MGH equals.
Yeah.
half.
Conservation of energy. The only thing I can think of when Mike came in here was the fact that you guys somehow got on the topic of fraternities and somehow labeled Aaron as the top choice of being in a fraternity.
That's a former thing of pain.
Oh, okay.
Already it has. It's been going.
It was like, I think it started over COVID, or maybe it started when I started being
Really?
free
This
stress.
is 4 years ago, probably.
Yeah.
It was like structures one.
Wow.
Structures
Oh,
two.
yeah, structures too. He was structures
He
too.
moved the time of the class that I signed up for earlier, so I showed up late every day. I
Ah.
was like, this is your fault, because I planned this. I didn't sign up for this.
I didn't sign up for this. Okay.
And
Then he made fun of you for being at the frat late
I don't
or
even,
something.
never been to this.
Oh,
Too late.
Yeah.
Then over COVID, all I heard was, oh, of course you got exposed. You just out partying.
Oh, that's so true. So true. Okay. Conservation of energy, right? We have MGH Well, we know that has to equal 1/2 mv squared. This being our potential. And this being our kinetic, right? Sort of this idea that right, we have to conserve energy as long as there's none lost to the system, right? We're gonna have this conservation of energy that happens through this travel of this ball in this example, right? From the top of our slope to the bottom of the slope, right? Well, if we think about, well, what is energy to begin with? It's equivalent to, right, the capacity to do work. Right, the capacity with work being, what's the definition of work? Yep. Force times distance. Energy being the capacity to do work, work being force times distance, right? We can relate these two. We will, as we move forward here. But we step back, because I think it's kind of interesting, okay? Actually, I think it's really interesting. Okay? Mechanics really developed along two branches. Any ideas what the branch is? First branch? One branch? Imagine it's developed by somebody, is concerned with something, and the output is both something. Newton is in this branch. There you go, Brandon. See that? Engagement. All right.
Wow.
He's got a positive there. Vectoral mechanics. That's what you guys were thinking, right?
I would never guess
You may have. It's to develop directly. Whoops. Don't want to erase things. Newton's laws of motion. This is the shit we deal with all the time, okay? It's concerned with, in vectoral mechanics, right? What are some vectors that we deal with in mechanics? Velocity would be one. Acceleration, you guys are deviating from the path here. Give me something else, right? What have we been dealing with elements?
I said
Forces. See, Amanda. +1 right there. Chalk it up. Forces. Or moments. James, you did say velocity, which is good, but we usually add mass to that, momentum. Right? Forces, momentum. Right? Both of these things are vectors. Right? They have a magnitude and direction. Branch 2. Any ideas what the second branch was? Or is? Are you really nerds out there? Nope. Analytical. Analytical. Originated by this guy, Gottfried Wilhelm von Leibniz. Okay? Badass. You know what this guy did? You guys took like 4 classes of this if you went to MSU. Four semesters of this when you first started. Calculus. Godfather of calculus right there. Alright, when he talks, you listen. Can't talk anymore though. Alright? Gone. Alright, momentum is replaced with what we would call this really cool vis viva, or what he called the living force. And it's what we call kinetic energy. Right. So this vis viva, 1/2 mv squared. Right. So now our force is now replaced by the work of the force. And these are scalar quantities. Okay? No direction associated. Well, that might become a problem, right? Because in mechanics, we are usually concerned with direction. We want to know both a magnitude and a direction of a quantity, so we can define a path, right? Well, as I mentioned before, we have this idea of conservation of energy. That's essentially our vis viva, right? Kinetic energy. So we have conservation. Of energy. Which gives us one equation to utilize, right? This conservation of energy. We have potential and kinetic.
Go after blank two.
What's that?
Yeah.
Looks like there's a blank for the question mark.
Oh, with 2 scalars. It's a game, James. It's a little like, what do they call it? Missing words or? Not a crossword, but Mad Lib. It's a Mad Lib. Could have put something else in there. A noun. Scalars. How can mechanics, which is concerned with direction, be defined by 2 chairs? Right. Well, we have conservation of energy. Right. Gives us one equation. Well, these badasses, Euler and Lagrange, they came up with this idea of the principle of least action. Now, I'm not a good writer, okay? Principal, P-A-L, PAL versus P-L-E. What's the difference?
Oh, this one should be,
Yep, this is Ellie's one.
This one should be L-E, so that's what I was thinking. But I have it written here as,
I thought that was like a British versus American thing. No,
It's like the person, right?
well, so I thought like P-A-L was the person.
Yeah.
Okay, that's what I was thinking when I did this, but then I wasn't sure. I thought I'd ask the
that's
audience.
fine, I knew that and I wrote it down the way you wrote it down.
Yes, see? It's easy to do. And you're gonna probably find a few more of those in here somewhere. So L-E, principle of least action. Okay. What's that? Oh, good. Well, we're gonna figure this out.
Yeah, it seems that is the case.
That is the case. So principle, just straight up, is like a position at a school.
Right. It's like,
What about like a principal at a firm? That'd be P-A-L also,
Yeah, I
right?
think that's also.
Okay.
leading position.
Assuming none of you guys are principals at a firm. Maybe someday. So if we knew the position, what's that?
You have to be an owner to be a principal?
Usually, some level of ownership. Right, DCI, I'm assuming, principals are owners. You guys dug into that at all?
I think they.
Got ambition?
Like a little, you know?
I think you have to buy in. Like, I think there's like almost like assistant principal and then a principal. There's like different levels.
Is it like making partner, you know, that's like
Yes.
a thing that people
Same
say?
thing, yep.
I made partner.
But in engineering firms, usually it's principal, I assume.
Yeah.
Unless you work for Morrison Merrily, you're all owners. Huh? Boom, right here. Still own stock in this company. And it's still growing and it's amazing.
Yeah.
They hate that shit, but I love it. Yeah. They wanted to buy me out when I left. I was like, mm-mm. I earned this shit. I'm keeping it. So then I keep calling them up every now and then, like, man, I hope you guys are working hard. I really need you to pump this up a little bit.
Keep growing.
Seriously.
You pay dividends?
No. It just appreciates year after year. Like, I think this year probably be like close to 25 grand. Isn't that nuts? What you get for killing yourself for a decade. So if we knew,
P1 at T1 and V1?
yeah, so we know the position at time 1 and the velocity.
Velocity one at T1.
Yep. So P1 and V1 at T1. And then we know the position at T2, okay? So suppose we know the position and velocity of a particle at T1, and further we know the position of the particle at some time T2. We could pick any number of paths, right? If we only knew those two things, right? Position, velocity. Okay, so this is a scalar. And then we knew the final location, right? And over some amount of time, right? We could have a whole number of paths that particle could take,
Assuming it doesn't stop.
assuming it doesn't stop.
Take a break.
Take a break,
Drink a coffee.
drink coffee, yep. Pull an
V2?
Elias.
Yeah, is there V2?
Nope. We don't know velocity at the second one. We could pick any number of paths to connect P1 and P2. Once we've picked a path, okay, conservation of energy, both potential, right, and our kinetic, right, that path will define those two scalars, right? So once we've picked a path, whoops. Conservation of energy. Will give us, right, both our potential and kinetic energy. Right? Potential equals, oops, equals kinetic. All right, so we started at this point and we knew what our path was, right? We knew the position of this, right? We do mgh, 1/2 mv squared. Right? At any point along this, we'd have conservation of energy going on. We could figure out what the potential and kinetic energy was at any given point. So that along the path, right, we can calculate the vis viva, the kinetic energy, right, as the integral along the path of the kinetic energy. And it's the integral of this kinetic energy that's essentially the action, right? What's actually going to happen. If we summed up every little point from point 1 to point 2 of our kinetic energy, right, we would figure out what the action of our particle is, right? And the principle of least action PLE of least action states that the actual path taken by the particle will minimize the action. Or make it stationary. Right? This is that idea of path of least resistance, right? So the principle of least action states that the actual path taken by the particle will minimize the action, or minimize the kinetic energy taken by that particle from one point to the other, right? So that's analytical mechanics and concept of energy, right? Well, what's this idea of variations? Well, the calculus of variations, okay? As we noted in the last section, right, this path chosen by nature will minimize or make stationary the integral of the kinetic energy over the path. What does that mean? Well, our action, if we look at this in expression terms, right? If we said the action was this variable s, that variable s is the integral from time 1 to time 2 of the kinetic energy over the time, right? This is an integral. Right? And the principle of least action says that that this action of this particle, right, is going to want to minimize, right? Well, regular calculus shows us how to find the minimum of a, what is it? When we take a derivative, we're finding the minimum of a function. Nice, Elias. A lot of confidence there. I like it. S is not a function, right? Any idea what they might call this integral of a function? Functional. That easy? And the calculus of variations is used to minimize a functional. Where a functional is an integral expression that implicitly contains the governing differential equations for a particular problem. Okay. Governing differential equations for a particular problem. Yeah. That is a functional, right? An integral expression. In this case, we don't have necessarily a differential equation here, but we do have a function. The integral of a function is a functional. And if we were using the principle of least action, we want to minimize, right, the kinetic energy. In this case, it's represented as this integral from point 1 to point 2. So minimizing that, right, that functional is what variational calculus is all about. So in order to set the, or to find the minimum, what we do is we set what they call the variation, the first variation of S equal to 0. Whoops. What am I doing? First variation of S equals 0.
Yeah, what is it?
It's like a partial almost. It's essentially just a variation.
The partial, but like not connected.
Okay, wow. You guys are super critical here. I'm so glad to record these and you guys won't be here to talk shit.
Well, we'll talk shit after when we're like, wow, this is terrible.
Well, it'll be so long. I know you guys' attention span is like not very long.
Well,
so-
no, we just put it on 2 times speed.
Oh, 2 times speed, yeah. I bet I sound great. Okay, so to find the minimum, we set the first variation of the kinetic energy, right? The action to 0. You got that little partial almost, right? Variation of S equals 0. Well, Euler and Lagrange, as badass as they are, they both independently found the first variation is a solution to the following differential equation where we have a functional. That functional, right, f, well, that f might be a function of y, the derivative of y, and x, right? It's a differential. So we have, right, each of these y's might be a function of x. So if we have this functional, Lagrange and Euler came out and said, hey, the first variation is the solution to this differential equation where you have the partial of f with respect to, that's a partial, Elias,
Looks like a back.
y. Well, shit, you guys come up here and draw a better one than that, okay? Doesn't that seem okay?
Looks great.
Thank you, Brandon. You know, Brandon gets 2 points today. All right?
Is that a capital Y?
Oh my God. Yes, the capital Y, right? Because we're talking about a functional, right? So this is an expression that's a function of functions, right? Where we have this function y, which might be a function of x, and that y, right, might have a derivative as part of it, right? A differential equation in here. And so, yeah, just y. It could be uppercase or lowercase, but I thought it was just differentiating. Okay, so the partial of f with respect to y minus d dx partial of f with respect to y bar equals 0. Why did I change from partials to derivatives? It doesn't matter, right? A partial is a derivative, okay? But that one right there. Okay? Enough said. What I do want to say is there's mathematicians, right? When I was developing these notes, I did a little research on like this Euler and Lagrange solution, okay? This is like the nerds love this, okay? Mathematicians love this. Anyone know this equation already? Okay. Hamilton, who's like this mathematician, and a bunch of other people said that this is mathematical poetry. Okay? Mathematical poetry. Make sure we get that down. I was just blown away at how much they loved Euler and Lagrange equation for the first variation. Okay? What does this give us? Well, this gives us what they would call the extrema, or which is really the optimum path, right? Because that's what we're talking about overall, right? Conservation of energy. We can figure out what this vis viva, right, or the kinetic energy of this particle as it travels from one known point to another known point. And when we use the principle of least action, the path taken is going to create the least action. And when we try to take the least action, we have to take the first variation and set it equal to 0. The solution to that is this. Okay?
Is this a different language, or is that just like?
It's Latin. It's Latin, my man.
Alright.
Kind of like those symbols on your fraternity. Greek is the same as Latin, right? Pretty much. Didn't it come from that? No? Damn it!
I was like, what?
I was like, it worked for a little bit, and I was like, I thought they kind of came from the same thing, but okay. Emily's saying they are not, so I'm gonna take her word for it. All right. Well, let's do a little example here, right? So that you guys got something to flex on when you're partying while I'm gone. Okay. Prove that the shortest distance between 2 points is a straight line. Right. So we have 2 points sitting in space, 2D plane. Okay. Sutton, you go back to TD and H. Tell Scott about this. Okay. A and B. These points you're gonna know. Y sub A, right? Y sub A, Y sub B. You know position of our points. Is your uppercase, Amanda? All right. We're going to consider any possible paths right? A to B, right? Where y is a function of x, right? We have some sort of line, and our location in the y-axis is some function of the x-coordinate, okay? Well, if we're looking for the shortest distance, we need to know, well, what is the distance of our path as we're traveling from A to B, right? So we need to know the length. Of the path in terms of the function y sub x, right? That defines the path, right? Y sub x defines the path. But we need to know, right, in terms of that path, right, what's the length of the path? Because we're lucky. Time's up. You wasted enough of my time. It's Elias's fault. It's Aaron's fault. I'm gonna call out. Who else? I'm gonna call out everyone but Brandon today. Okay.